Good morning, everyone. Hope you guys can hear me okay. We're on page 5 of our notes. So we're just going to talk about two topics here: average value theorem and the second fundamental theorem of calculus. So we'll just work through these 2 pages of notes and then maybe just do 1 or 2 practice problems. Hopefully you guys will find this pretty straightforward. But we'll just start off with our notes here. So average value theorem is considered the mean value theorem, but for integrals. If you remember from first semester, mean value theorem is where we're trying to guarantee a specific slope on the curve, right? If a graph is continuous and differentiable, and we identify 2 points on the curve and we find the slope between those two points, then whatever slope exists between those 2 points, I can guarantee that the slope is going to have to show up somewhere along the curve as well. So if there's a slope of 1/2 here, the curve is going to have to exhibit a slope of 1/2 at least once somewhere along the curve. Right? Or if this is a slope of 2, then there must be a slope of 2 somewhere. So we can guarantee a slope, and that's what mean value theorem does on the curve for us. But average value theorem is more about guaranteeing a specific y value across a curve. So we know that what an integral represents, definite integral represents area, right? So we know that the integral from a to b of f of x dx will give us information about, assuming that the whole graph is above the x-axis. It'll give us, let's say this is a and this is b. It'll give us area of a certain region. So this is really just a rearranging of an area formula for rectangles. So if we think about what an area formula looks like for rectangles, we know that area is basically width times height. Width times height of a rectangle equals the area of that rectangle. So imagine if I wanted to solve for height instead. So if I want to solve for height, I can simply divide both sides by the width, right? So we know that this equation is true. Height is simply area divided by the width. So that's basically what this equation is doing. F of c represents the height, or in this case, the average height of our curve. The integral from a to b of f of x dx represents the area. And then you notice how it's divided by b minus a, but that divided by b minus a is getting pushed out in front. So it looks like a multiplication, but really it's the area divided by the width. It's just written out as a coefficient instead of below the integral here. So height equals area divided by the width. So if I want to find the average height amongst all these heights on the curve, I'm going to take the full area of the shaded region divided by the width, and then whatever average height I get is my answer. So it's basically averaging out all these different heights and finding that average height for us. So we call that average value theorem. Okay, we want to find the average value or the average height across my interval. We can also think of it this way. There exists a rectangle such that the area of the rectangle is the same as the area under the curve, and f of c is the height of the rectangle. So we can kind of imagine taking this shaded region and forming it into some rectangle that also shares the same area as this shaded region of the shaded region of this curve. So example one, find the average height or average value of this function between the x values of 2 and 5. So we're simply just going to follow whatever this formula says. My 2 and 5 are my a and b values. So let me write the full formula again, and then we can just plug in information as we see it. So I'm trying to find my average height or average value. So f of c equals, my a and b values are 2 and 5. Definite integral from 2 to 5, again, a to b. My f of x is the x squared plus 1 dx. So again, the big picture is we're going to find the area of the region divided by the width. And whatever we get in return is the average height amongst all those y values on the curve. Do a little bit of cleanup. 5 minus 2 is just 3, so that's 1/3. Now, again, we have to be careful with how we do definite integrals. We typically want to read from left to right, but we're not going to apply the process from left to right. Again, the bounds is the last thing that we do. We're going to take care of the indefinite integral first. We're going to go through power rule, evaluate, find the antiderivative, and then plug in the 5 and 2. And then I can work in the 1/3. Now, the 1/3 you can distribute right now if you like, get it part of the expression, but I'm just going to leave that to the end. I'm just going to take care of my integral without the bounds, then the bounds, and then at the very end, I'll just distribute that 1/3 through. Okay. So I'm going to treat this part of my problem first. Okay. Both terms are ready for power rule. We'll go through power rule. Add 1 to the exponent divided by the new exponent. The 1 becomes an x. Again, there's no plus c if we're dealing with definite integrals. The plus c will just end up washing out or canceling out. Now that we have our antiderivative, we can now work in the bounds. So half bracket on the right side, 5 on top, 2 below. Remember, upper bound always gets evaluated first, so the 5 gets plugged in for all the x's. Once the upper bound gets inserted for all the x's, then we do a minus, big parentheses, and repeat the same process for the lower bound. So 2 gets plugged in for the x. Now this is the result of this piece right here. Okay, we still haven't done the 1/3 yet. We'll do that a little bit later. But I'm going to just plug this in the calculator here, add those numbers together. I get 125/3 plus 5 minus 8/3 minus 2, and that ends up giving me 126/3. But I'm not quite done yet because this is the area, but I'm trying to find the height. So I'm going to take my area, divide it by my width, which is same thing as multiplying by 1/3, and that will give me my average height. So therefore, I can say f of c is equal to 1/3 of 126/3. Basically, area of the region divided by my width of 3. And this ends up giving me a nice whole number. It may not always, it may give me a decimal value, which is fine, but this is telling me the 14 is now this is my average height. So across all my different heights across on this curve from 2 to 5, if I were to average out all those y values, the average height amongst all those y values will be 14. That's part A. Just to give you a perspective in terms of what we've found, this is what our graph looks like. X squared plus 1 is a parabola with a y-intercept at 1. So we're only looking at the graph from 2 to 5. And this is not to scale, obviously, but if we were to average out all these heights from 2 to 5, the average height is going to be 14. That's what we found. Okay. The average height amongst all these y values is going to be 14. So that's what we found for part A. Now part B is asking find the C value. So it's asking, okay, wherever we know that if the average height is 14, the graph has to hit 14 somewhere, right? The graph can't have an average height of 14 without actually reaching that height of 14 somewhere along the path. So we're just basically asking, okay, when is the graph actually going to hit that y value of 14? And so that's as simple as taking the function and just plugging in for y and solving for x. Okay, we know what y value we're trying to target, and we're just asking the function to tell us the location of that height. So part B, find the C value. And C value is basically your x value of your solution. So my function is x squared plus 1. You can just take that average height that we already have, put it in for the f of x and for the y, and we're just going to solve for x. Subtract 1 from both sides. 13 equals x squared. Take the square root. Plus or minus shows up. Now, square root of 13, just for reference purposes, ends up being around 3.6. So around 3.6, again, my graph is not to scale here, is where that graph is going to hit 14. Now, the reason that we get plus or minus root 13 is because this is a parabola. So the parabola is also going to hit a y value of 14 on the other side of the y-axis. So it's going to be plus or minus 3.6. However, we only care about our bounds here. So our bounds is between 2 and 5. So we only are looking for a C value between 2 and 5. And the only one that makes sense is 3.6 or a positive 3.6 or root 13. So therefore, our C value is root 13. Okay, we're just finding the x value location where our graph is hitting that average height of 14 along its path. All right, next page. So number 6, page 6, next topic is second fundamental theorem of calculus, which I abbreviated as SFTC. As a brief reminder, we know first theorem of calculus, which is just really definite integral. I know that if I want to find the integral from a to b of some lowercase f, it'll turn into the antiderivative and then plug in my upper and lower bound, whatever that antiderivative is. That lowercase f to uppercase f just indicates the process of the antiderivative happening. Now, second theorem is exploring the idea that derivative and integrals are just opposite operations, that they are like addition versus subtraction. It's like multiplication versus division. They have a way of canceling each other out. So that's what we're going to explore on this page, that we can use that inverse relationship to help speed up our process and solve and find our answers a little bit more quickly, because if we know two things will cancel out, we can skip past a lot of the process knowing that they will just end up canceling or zeroing each other out. So now to recap what we've covered indefinite general integrals. This is area finding function. This is where we find the indefinite integral and we have a plus c that shows up. You saw this on your quiz. We also did definite integrals, where we're finding the area between two x values and we find the antiderivative and then we plug in the upper and lower bound, kind of like what we just did on the previous page with average value. There's also now a function that is the integral itself. Instead of going from a constant to another constant, we're going from a constant to a moving value of x. So now we can define a function as the definite integral of some f of t. Now this feels complicated, but we're going to use second theorem to make it a little bit easier to work with. So just understand that this is really saying that this function is living at the antiderivative level of f of t. So these two functions are really staggered in terms of I need the integral of some function to raise it up to another function. So these two functions are kind of derivative relationships with each other. So here's a second theorem. It applies to the concept that derivative and integrals are inverse operations of each other. And let's say we have an integral of f of t dt. And then we took the derivative of that definite integral. I know this looks really complicated, but the nice thing about this relationship is that if I'm applying opposite operations on the same function, they're largely going to cancel each other out. So the big picture is that the derivative and integral are going to kind of wipe each other out. It's like adding 3 and then subtracting 3, right? If I add 3 and then subtract 3 from the same starting point, I'm going to be where I started at the beginning. Now, even though I cancel these operations out, there is going to be some residual impact from this upper bound. So what's going to happen is this function is not going to change much, but this upper bound is going to feel the impact of these two operations being applied. So what's going to happen is the upper bound is going to get inserted into the function. That's the effect of the integral here. It's going to end up plugging that function in. And then the impact of the derivative is that the upper bound is going to turn into its derivative. So the reason why this is a shortcut is because rather than doing the full antiderivative, then plugging the upper and lower bound, and then turning around to find the derivative, we can just skip to the end and know that the upper bound is going to have a little bit of impact, but largely the function is not going to change much. It's f of p of x times p prime. I'll talk about the second theorem or the second application a little bit later. Let's look at some of these examples here. If I want to find the derivative of the definite integral of root t squared plus 4, we're going to, again, second theorem is we want to use second theorem because we want to avoid having to do a full integral process and then find the derivative. So we can skip a lot of steps here, knowing that these two operations will cancel each other out. So again, what we do is we're just going to plug that upper bound into the function, upper bound into the in for t. So simply just going to be square root of x squared plus 4. That's what this is saying, f of p of x, times the upper bound's derivative. So x's derivative is 1. So just square root of x squared plus 4. Now, normally we can't just plug the upper bound into the function, right? We saw that from the previous page that I kept stressing. Oh, we can't just plug up upper bound into the function. We got to go through the antiderivative first and then plug in the upper bound and lower bound. But the reason that we're able to do that here is because there's a derivative that's going to come right after the integral. So we know that this is not just one operation here. These are two opposing operations canceling each other out, and that's what's causing that x to get plugged in. Okay, so normally if it's just a definite integral, we can't just plug that upper bound into the expression. We have to do some calculus procedure here before that upper bound gets plugged in. Now, a common question is, well, what happens to this -3 here? How come we don't do anything with this -3? The reason why is because when that definite integral gets applied, that -3 will get plugged in and it'll end up being a number. And that number is going to be zeroed out because the derivative is just going to take whatever constant this produces and zero it out. So whenever you see a second theorem procedure here, your constant is not going to have an impact because it's going to produce it's going to produce a number, and then that number will get zeroed out by the derivative. All right, part B. Again, we have a derivative, an integral operation, opposing operations on the same expression. So we can apply second theorem. Again, the root t minus 1 is not going to change much. No need for power rule, no need to find the derivative. We just have to follow the rule here. So the upper bound will get plugged into the function. So the x squared will replace the t. And then we multiply by the upper bound's derivative. So times 2x. And that's it. Part C. If you look at part C and part B, exact same problem. It's just the lower bound is different. And again, just want to prove to you that the lower bound has no impact on the process because the upper bound will get plugged in times the upper bound's derivative. And the 3 and 10 will produce some number, but that number will zero out. So part B and C will be the exact same. Upper bound into the expression times the upper bound's derivative. So that lower bound constant is not going to impact the answer. Part D, I want to apply this rule here because we see derivative and definite integral being applied, but something feels a little bit off. And what feels off is the fact that my lower bound is now a variable and my upper bound is the constant. And I want to have them in the order that the rule tells me. So we talked about last Thursday how we can change the bounds if we want. We just have to adjust for that change with a negative. So I'm going to rewrite this problem here. This is the same thing as finding the derivative of a definite integral from 0 to 3x. And then I'm just going to pull a negative in front of my expression. Doesn't matter if I put it numerator, denominator, or outside. But I'm rearranging the problem. I'm not changing the overall value. I'm just making it easier for me to follow my rule. So now I'm going to follow what my rule says. Derivative and integral cancel each other out. My upper bound will get lodged into the expression. So negative 1 over 3x plus 2. Again, all we're doing is we're taking whatever variable is in the original problem and replacing that variable with the entire upper bound. Times, so we've done the f of p of x, times p prime, so times the upper bound's derivative. So 3x derivative is just 3. So there's our resulting answer. Let me clean this up. Part E, what's different about part E is now both my bounds are variables. So we basically are just going to apply the process twice. Okay. So what the second rule says, if both my bounds are variables, I'll do my upper bound just like how I did from before, f of p of x times p prime. But then the lower bound is also a variable, so it will also have the full impact, or it will also stay within my expression. So what's going to happen is it's going to be minus, and then we repeat the same process for a lower bound, f of q of x times q prime. So now part E, we see derivative and integral process canceling each other out. So f of p of x, plug the upper bound in for t. Times the upper bound's derivative times 2x minus, normally this is a constant, but in this case it's a variable, so we know it's not just going to go away. It's going to have some, it's going to leave some term for us because it's a variable. So do the same thing with the lower bound. Lower bound gets plugged into the variable. So that's what this is doing here, f of q of x. Plug the lower bound in for the variable of the expression. Times the lower bound's derivative. X's derivative is 1. So I'm going to clean this up here. I get 4x cubed plus 6x. Distribute the negative through, minus 2x minus 3, which is equal to 4x cubed plus 4x minus 3. Now, what we did here was I introduced to you the shortcut before the actual process. Okay, we don't want to do the actual process, not when the shortcut is available, but I do want to kind of show you what that full procedure looks like so that you can recognize this as a shortcut form, a shortcut that we want to take advantage of. So I want to do part E again, but do the full process. And I want to show, how much longer that can be and how this process is getting the same answer as if we were to do it this long way. So if you have any space, I think you use space in 6B or 6C for us to work through this problem with the full procedure that we know with power rule and everything. So I'm going to try part E again. But using the process that we've learned from previous sections. Now, initially, we're going to ignore that derivative, right? We're just going to, let's approach this problem like how we normally would, right? We'll do the full integral, find power rule, plug in the upper and lower bound, and we'll turn around and find the derivative and see if that matches up with the shortcuts that we learned with second theorem. So we know that if we want to do the full integral process, we always ignore the bounds. All right. So we'll do power rule first. 2t becomes 2t squared over 2. 3 becomes 3t. The 2's cancel out. And now let's evaluate the bounds. Okay, right? So we're doing the indefinite integral first, and then we'll work in the bounds. So my lower bound is x, my upper bound is x squared. Upper bound gets inserted into my expression, so x squared squared plus 3x squared minus lower bound gets evaluated plus 3 times x. So this is the result of this. We haven't done the derivative yet, but let me clean this up here. X to the fourth plus 3x squared minus x squared minus 3x, right? I'm distributing that negative through. X to the fourth plus 2x squared minus 3x. So these are all equivalent, right? Integral, definite integral, the result here. So now let's turn around and find the derivative, right? If I want to find the derivative of this x to the fourth plus 2x squared minus 3x, power rule, x to the fourth becomes 4x cubed, 2x squared becomes 4x, and then minus 3x becomes minus 3. So we get the same answer both ways, but we prefer the shortcut because if we know our two operations will cancel each other out, then why do the full process and undo it? If we know, that we just follow these simple rules, we will know what happens to these upper and lower bounds without having to go through the full process. So we would much prefer going through this method rather than going through a full procedure and undoing it, right? It's like the process of, if you know that you're going to be adding 3 and subtracting 3, rather than spending the time adding 3 and subtracting 3 to the function, you know that you're just going to be left with what you started with and just cancel the 3 and negative 3 out. It's kind of like this here, but with calculus procedures, right? So we'll much prefer going through this one-step process or two-step process rather than going through a full power rule, upper bound, lower bound, and then find the derivative. Okay, let's just do one example of average value, and then we'll do another example with second theorem, and then we'll be done. Okay, so we'll just do 6b and 6c. So number 47, this is on practice problem on page 6b. We're going to find the average value going through average value theorem. So first step, plug everything in. A and B are negative 2 and 2. Do some cleanup here. I get 1/4. I'm basically reading this from right to left here. I'm going to take care of the antiderivative, then plug in the upper and lower bounds, get that number, and then multiply everything through by 1/4. So ignore the bounds. All right, let's do the calculus procedure here. We'll go through power rule. 4 becomes 4x. X squared becomes x cubed over 3. Now that we have the antiderivative, we can work the bounds in. Upper bound first. Minus big parentheses. Repeat the same process with lower bound. 4 times -2 is -8. Put that in the calculator. Okay, so 32 over 3. Now, we're not done yet. We have the area component, but we still have to find the height, the average height amongst all these y values. So we have to still multiply by 1/4, right? Which ends up being 8/3, 32 over 12 or 8/3. So that's part A. So that means if we were to compare all the y values on the curve 4 minus x squared from -2 to 2, my height amongst all my y values will average out to be 8/3. So now part B says find the C value. So now that we know what our average height is, where's the location of this average height? So that's what part B is asking. What's the location of this average height? We know that's our y value, but what's the x value at that location? So we can simply plug 8/3 into the y and then solve for x. So we get 4/3, x squared equals 4/3, because this is going to be 12/3 minus 8/3, which is 4/3. Take the square roots. So C is equal to plus or minus 2 over √3. But we know that we only are looking at values between -2 and 2, and I think both may work. Because this is plus or minus 1.15, and they both land inside my interval. So sometimes we do have C values where multiple solutions are possible. So we have 2 locations where the graph is going to reach the average height of 8/3, and they're both landing between -2 and 2, so we keep both of those values. Okay, next page. Let's do a second theorem problem. So we do want to take advantage of second theorem because we don't want to find the full antiderivative of this, plug in the upper lower bound, get the number, get the expression, and then turning around and find the derivative. We're going to try to skip past a bunch of that process, knowing that these two are just going to cancel each other out for the most part. Okay, so if I want to follow second theorem, I would prefer my variable to be up top. So I'm going to take the time to flip the bounds, get myself ready for my second theorem, which is f of p of x times p prime. Sorry, this got cut off here. Let me rewrite this. All right, so now that I have everything lined up nicely, my lower bound is the constant, my upper bound is the variable. My constant is not going to play a role. It's just the upper bound that's going to be involved. So I know that these two operations will cancel each other out. There's no need to do an antiderivative process here. Just have to take the time to plug the upper bound into the variable. So every t that we see, we replace with 2x cubed. I'll clean this up later, but this is basically representing my f of p of x times p prime. So I still need to include the derivative of that 2x cubed. It is getting impacted by the derivative, even though it is canceling each other out. So times 6x squared. So again, this is my f of p of x. And then this is my p prime. All right, let's see if we can clean up a little bit here. So I get negative 4x cubed times 6x squared. It's going to be negative 24x to the fifth. And then this is 5 minus, I'm going to distribute that exponent through. So 2 squared is 4. 3 times 2 is 6. So we add exponents here. This is x cubed times x squared, but here we multiply the exponents because there's only one variable and two exponents are next to each other. Okay, any questions? Eventually, I am going to check the homework for 4.3, 4.4, and 4.4b. You guys picked up the homework packet before we left school here. But I'm not going to make anything due tomorrow. But I will try to work on the keys for these so that if any of you want to get a head start with homework, you can. But basically, these are just homework pages from the textbook, but I put it in the homework packet so that it'll be easier for you to just work off of the pages. But I'll work on that. I'll also send you a link for the video, but it's going to be on the Unit 4 page. Okay. All right. Thanks, everyone. Hope you guys have a great rest of your day.